Okay, so this video is going to be on the periodic table trends. As you watch this video, I highly recommend pulling out your periodic table. So we're going to start with something called the atomic radius. And the atomic radius is the radius of the atom measured from the nucleus to that outermost electron. So if we look at that Bohr model idea, we have that nucleus, we have maybe 2 electrons in that first ring, second ring, maybe we have 8 electrons somewhere in there, or 6, whatever it is. So we're looking at that distance of that nucleus and then that outermost electron. And so here's some example of those right here. And so I'm actually going to flip to the next page to give you a better idea. So this is showing the different atomic radii of different elements. So you'll notice as we go down the periodic table and across, we are increasing our atomic radius. Okay, so I do also want you to be aware of the ionic radius. That is the radius of an ion. So that's after it's gained or lost electrons. So it's that plus charge or the minus charge. And so what you'll find is cations are smaller than their original metal and anions are larger than their original metal. So I have this example here of that lithium atom. Okay, and then lithium plus 1 is actually smaller, and it's smaller because it's lost that electron. And then I have this other example here with chlorine. So here's the chlorine atom, and it's going to be smaller than the chlorine atom after it's been ionized because it's going to grow in size a little bit. With that extra electron, it's going to take a little bit more space. There's a little bit more detail that you can get into at the higher levels. So then the next trend is ionization energy. On your periodic table, it's written as first ionization potential. You'll find that there are actually second, third, fourth different ionization energies. We're going to focus only on the first one. It is the energy required to remove the most loosely held electron from the atom. So the more easily an electron is lost, the lower the ionization energy. You'll notice the trend increases as we go in this direction. So increasing ionization energy. And this is going to link back again. If we look kind of at that Bohr model idea, we got some electrons in that first ring. Let's say we have 2 electrons in this outermost ring. What you'll find, actually, let's do 2, 4, 6. Okay, that's 2 rings. Here's our third ring. Let's say I only have 1 outermost electron. So that's similar to an alkali metal. What you'll find is it's really willing to give up that outermost ring because it can't have the full 8 of that full outer shell. And everything would like to have 8 electrons in their ring if possible. It makes it most stable. So if it only has 1 ring, it's going to really be easy to take off. Whereas if we look at something like a halogen, its outermost ring is going to have 1, 2, 3, 4, 5, 6, and 7 because it is a halogen. And so it's not going to want to give up an electron. It would rather add an electron. So this is a graph that I'm having you explore in the lab as well. And what I want you to notice is the peaks are your noble gases. Okay, and so it should make sense that a noble gas has a full outer ring, so it's not going to want to gain or lose an electron to fill the outer ring. Whereas the elements on the bottom here, these are our alkali metals. Okay, so our alkali metals, and they totally want to give up an electron because by doing so, they'll have a full 8 in the outer ring. Also notice these segments in between. These are the different periods on the periodic table. And notice it is also color coded with the S, P, D, and F blocks. Next trend is electron affinity. This one's a little bit goofier. Instead of plucking an electron off, it's the energy released when an element gains an electron. So it's going to have a similar, if we generalize it, increasing in this direction. However, notice that the noble gases don't do anything. You have more exceptions. But in general, we're going to say it increases electron affinity in this way, and that is gaining an electron. Okay, next trend is electronegativity. We're going to come back to this one a lot. It is a chemical property that describes the tendency of an atom to attract electrons. So what you'll find is fluorine is super electronegative, and it's going to pull its electrons towards it. So when we generalize this trend, we usually say we increase electronegativity towards fluorine. And we're going to come back to this when we do bonding as well. Now, with all these properties, I want you to be able to compare something like calcium versus bromine. Tell me who's more electronegative just by knowing that general trend and without looking at numbers. So if you look here, here's calcium, here's bromine. Calcium is on that other side, so we know that bromine is going to have a larger electronegativity. So that's ultimately where I want you to go with these. Next trend is reactivity, and it has to do with how readily metals lose and nonmetals gain electrons. Usually I'm going to write reactivity this way. I think that's a little bit easier. Notice metals get more reactive towards francium, nonmetals become more reactive towards fluorine. I like to think of that alkali metals, how it's super reactive with water, and as we progressively went down the periodic table, got more and more reactive. Next trend is metallic character. So that's related to that reactivity. Again, notice it's the same trend. Francium is their most metallic, your least metallic being fluorine. And then the next trend I want you to know is basically oxidation numbers. And I want you to write these down on your periodic table. Oxidation numbers have to do with how many electrons are gained or lost by an element. They're also the basis of what we'll be using for formula writing and naming. So notice group 1 is +1 for its oxidation number. Group 2 is +2. Group 3 is +3. Group 4 is usually plus or -4. Group 5 is -3. Group 6 is -2. Group 7 is -1. And group 8 is 0. So I do want you to write these on top of the periodic table. And then what you're going to find is how this all comes together as we start the next unit. Now, this is more what we're going to hit in the AP level or college level. I'm not going to test you on this. I just want you to be aware that there's actually ways to explain these periodic table trends, and we usually use something called effective nuclear charge and electron shielding. And basically what the effective nuclear charge has to do with is seeing how much positivity is felt in the nucleus by different atoms. And then electron shielding has to do with electrons blocking the ability of other electrons to feel each other, and so they don't feel that positive charge. Okay, so if the shielding, if we have a nucleus here, and we have an electron hanging out over here, and this electron that's over in this next ring can't feel that positive charge from that nucleus because of this guy blocking. So that's that shielding effect. And so those two things we can use to explain a lot of our trends. So as we go up and across the periodic table, we find that it has an increased effective nuclear charge. And so what that shows is that as we're increasing the positivity, that links to why we have these increasing trends of electronegativity, electron affinity, and ionization energy. Okay, so in general with the periodic table, I do want you to be able to just generally characterize that we have increasing electronegativity, ionization energy, electron affinity, all in that direction. Usually I would say increasing atomic radius in this direction, and then reactivity or metallic and non-metallic character would be in the middle. So those are the main trends. And so if I ask you something like Be versus oxygen, who's going to have a larger atomic radius? And you go, okay, I know my arrows are down in this direction. Be would have a larger atomic radius. Or if I compare, let's say, Rb with oxygen, who's more electronegative? And knowing this trend, you would realize, oh, oxygen is closer to fluorine, therefore it's more electronegative. Also, I skipped over this slide here on Coulomb's law. This also goes together with that effective nuclear charge. I just wanted to explain it first. So the force that is felt has to do with the effective nuclear charge divided by the distance. So this actually goes together with your radius size. And so things can get way more complicated. I just want you to know the term Coulomb's law and know it has to do with force equals charge over distance. Okay. And so that again helps explain the trends. But the way I will test you is with questions like the Be versus oxygen. Or if I ask barium versus chlorine, who's going to have a higher electroaffinity? And you would say, oh, it's chlorine because it's closer in that arrow direction.